Now, motion diagrams, I am probably never going to draw a motion diagram for you, but figure 2.8 does have something interesting. It shows the position as a function of time, and it highlights once again how the instantaneous velocity is the slope of the position versus time graph, and how we can read that. And this is something I do expect for you to be able to do. So if we're drawing our position as a function of time with that blue line, and we look at that and we just eyeball a slope off of it, we can see that the slope is positive, and that tells us that the velocity is also positive. We continue along with our blue line, and at point B we draw our tangential instantaneous velocity. It's also positive, so the x velocity is also going to be positive. At the point where the position graph has an inflection, the slope is 0. There's a horizontal line, therefore it has a slope of 0, and the horizontal velocity is 0. And similarly on the last 2 points, the slope is going to be negative, and so the x velocity is always going to be negative, or it's coming in the negative, the velocity is in the negative x direction. Now, acceleration is simply the change in velocity with time. I mean, if you're sitting at a stoplight, you hit the gas pedal, then your velocity was initially 0, and then after some amount of time, your velocity is now what, 30-40 miles per hour? You have accelerated. So it's a change in velocity divided by the change in time. And now if we look at our velocity versus time graph, we can simply recognize, knowing what we know about the position versus time and the velocity, that the slope, the change in time with respect to the change in velocity, gives us that slope right there is our acceleration, and the same with this instant, and the same with that instant, and so on and so forth. The slope gives us our acceleration, and you can see that the slope is positive here, and looking down here at our acceleration versus time graph, we have a positive acceleration corresponding to that positive slope. The slope is negative here, and so we have a negative acceleration. Again, negative acceleration, and now positive slope, positive acceleration. The only thing I really want to mention on this slide is we've already defined our average acceleration to be the change in velocity divided by the change in time. And if we take the limit as the change in velocity over change in time, as the change in time goes to 0, then guess what? We get our instantaneous x acceleration, or the derivative of velocity with respect to time. Much like you'd expect from what we already know about our position versus time graphs, if we look at our velocity versus time graphs, and I look at 2 points, P1 and P2, my average acceleration is going to be the change in position divided by the change in time, or change in velocity divided by change in time. Over here I've got my change in time. The average slope is simply the slope between those 2 points. The instantaneous slope would be looking at this slope as delta t approaches 0, so now we're looking at the tangential slopes. So here we have the instantaneous acceleration as a function of time in red. Now, there's a lot to talk about on this slide, and again, I will reiterate that I'm probably never going to draw motion diagrams. However, do take a second and pause on this slide and convince yourself that you know what's going on. Here we're looking at position as a function of time. And I've already said if the slope is positive, the velocity is going to be positive. And what I'd like to talk about now is the curvature of this position versus the time graph. The curvature tells you something about the acceleration. If it's curving in the upwards direction, then the acceleration is going to be positive. If there is no curvature to the position versus time graph, then the acceleration is going to be 0. Similarly, if the curvature is downward, then the acceleration is going to be in the negative direction, and so on and so forth at point D and E. So please take a moment, pause this, read what you're reading in blue here, and convince yourself that you can do this, because this is an extremely powerful tool that I will expect you to be able to use, looking at the curvature and the slope of position versus time graphs to learn something about the velocity and acceleration. Motion with a constant acceleration is a lot more simpler, because we can write the velocity. It's going to change at the same rate throughout the period of the motion. For example, if you consider an object that starts from rest and it accelerates, perhaps your car from the stoplight, then for every increment of delta t, we can even just say that delta t is maybe a second or so. The velocity is going to increase by the same amount as the acceleration. So at 2t it's going to be twice as long, at 3t it's going to be 3 times as long, and at 4 delta t it's going to be 4 times as long. So the velocity is going to increase at the same amount for each time interval. That's constant acceleration. Now we also know that the velocity is the derivative of the position with respect to time. Now I'm talking about the instantaneous velocity. And if we look at a velocity versus time graph, we know that the slope of the velocity versus the time graph is the acceleration. For those of you that have had calculus, if you integrate both sides of this with respect to dt, then the integral of the instantaneous velocity with respect to time, that's simply the area under the curve, and that is equal to the position. So the area under the velocity versus time curve is also the position. Now if you haven't had calculus, don't worry, I'm not going to beat you over the head with that. So we can write our equations of motion with 4 very important equations right here. And this slide is very important. Make sure you pause it and write these 4 equations down. These equations describe the velocity, the position, and the acceleration as a function of time. And wherever you see a naught symbol, x naught, v naught, that means the naught indicates initial. And the x subscript down at the bottom, or even the x right here, that means we're talking about the x direction. So moving left and right. If you wanted to talk about motion in the vertical, say up and down, then anywhere you see an x in any of these equations right here, simply replace it by a y. And you can apply these same exact equations to the y direction. Now, just kind of an aside, if you don't know the acceleration and you know the position and the velocity, then you'd want to use this last equation right here, But in general, these three equations up towards the top, they're the ones that I find that I can get by with for any of the problems that we're going to be solving. So let's take a look at using one of these equations. Now, in solving one of these problems, the first thing you want to do is say, what do I know and what don't I know? So here we are, we're looking at a motorcycle rider, and we know that the initial position is going to be 5 meters, and we know that the initial time is going to be equal to 0. And we say, hey, this motorcycle rider, he's starting at 15 meters per second, and he's accelerating. He's accelerating means that his velocity is going to change. So his final velocity is not going to be 15 meters per second. We know that it's going to be faster because he's accelerating in the same direction as his velocity. So this is something that we want to know. We want to know how fast he's going at the end of some period of time, and we know what period of time that is. That's 2 seconds. The other thing that we want to know is how far did he travel. So let's start with the velocity. So we want to know what his final velocity is equal to. And so we go up here and we take a look at our equations and we say, alrighty here, which one of these equations deals with velocity? And we're going to come up with that one and that one. Both of those have the final x velocity in them. Now if you look at this one right here, you're going to say, okay, well that one requires that I know the position, and I don't know what the final position is, so this equation is probably not the one I want to use. I probably want to use this guy right here. So if I write that as v0 x plus ax t, and you say, okay, well I know t, this would actually be delta t, or t2 minus t1. Since t1 is equal to 0, delta t is actually equal to t, which is 2 seconds. I also know how fast I was accelerating and the initial velocity, so I can simply go ahead and I can plug these guys in. I can say 15 meters per second plus 4 meters per second squared multiplied by 2 seconds. And you can also see here that this second squared cancels out. So right here I have meters per second, right here I have meters per second. So I'm probably doing something right here. So you go ahead and you pack that into your calculator and you come up with 23 meters per second. And that's how you solve the first part of that. Now, in order to solve the second part of that, we go back up here and we take a look at what we know, and we want to know the final position. And we have two equations that deal with that. Now we have the bottom two equations. Let me get rid of that. And we could actually pick between either one of these two, because now we know the final velocity, we know that, and we know those two, and we know that. So we could actually solve this equation for this, but that would actually be a little bit more algebra than I really want to do. This one we have explicitly written as something we know, and things we know. So that's going to be initial position plus velocity times time plus 1/2 acceleration times squared. And now we can go ahead and write our initial position, which is 5 meters, plus our initial velocity, which is going to be 15 meters per second, times time, which is going to be 2 seconds. And again, the unit right here, seconds, is going to go away, and we're left with meters. And then 1/2, the acceleration is 4 meters per second squared. and the time is 2 seconds, quantity squared. And again, the seconds squared is going to cancel the seconds squared, so the unit here is going to be meters. And then you go ahead and you type that into your calculator and you come up with 43 meters to be the position traveled by our motorcycle. So that's a classic example of something moving with constant acceleration, and we're able to solve for two things given some known quantities. Now, we can have two bodies with different accelerations. For example, if you're driving up Route 11 at a constant velocity, maybe you're a little over the speed limit, who knows, and we'd say your velocity would be 15 meters per second. And if we look at how your position changed as a function of time, since you're moving at a constant x velocity, your x position is just simply going to be a constant. Now suppose Mr. Police Officer sees you and thinks that you're going over the speed limit, even though you're not. He's initially at rest, and he is going to start accelerating. Because he's accelerating, he's changing his velocity, and he's changing his position such that we can write it as v0 t plus 1/2 at squared. And if you recognize that right there is a quadratic, and so our position is going to look kind of like a quadratic, and the officer is going to have a position that increases not linearly with time, but quadratically with time. And example 2.5 is going to say when does the police officer actually catch up with you? And then you would say that's when x of the police officer is equal to the position of the motorist. And I've written this guy down here. This guy right here, you use the equation for position and assume constant acceleration, and you would actually be able to solve for the time at which the police officer caught the motorist. Now, freely falling bodies, that is a classic example of something with constant acceleration. We define free fall to be the motion of an object under the influence of only gravity. So an object's going to be accelerating, it's going to be accelerating towards the Earth due to gravity. Now, the gravitational acceleration is 9.8 meters per second squared. Very important number to remember. We're going to use that a lot. And also it's going to be downward. So if we look at a cue ball that is dropped initially from rest, and we would find that to be our initial position as well, then the ball is going to be accelerating. The velocity is going to be increasing each time by the same amount as that of gravity. So with a constant acceleration, it's going to increase linearly. And the position traveled is going to be increased quadratically, as I described in the last problem. Now, a little bit of history here. A long time ago, Aristotle thought that heavier objects would fall faster than light ones, and his theory was that force was proportional to velocity. This is the symbol for proportionality. It means force is equal to some constant times velocity. But a very smart guy by the name of Galileo conducted an experiment off of the Leaning Tower of Pisa, where he dropped a heavy object off and a light object off, and these two objects he found fell at the same rate, neglecting air resistance, of course. And he was able to measure that rate at the acceleration due to gravity, which I mentioned on the last slide. Again, Very important, this number. We're going to be using this number a lot. And you can follow example 2.6 for an actual calculation of how much the velocity and position changes. The next slide will do this also a little bit as well. So if we look at an object under free fall, it's going to be accelerating due to gravity, which is going to be 9.8 meters per second squared. And if we choose our reference frame such that this is the positive y direction and this is the negative y direction, then our acceleration would actually be negative 9.8 meters per second squared. All the negative means is it doesn't mean it's decelerating, it means that it's accelerating the downwards direction. So our initial position would be 0 at 0 seconds. It's not moving, you haven't released it yet, but the object is experiencing some acceleration. Now, after 1 second, the object has lowered its position towards the negative y direction. 1 second later, and the velocity has increased such that velocity is equal to the initial velocity plus the acceleration times time. That's equal to 0. So we can see the velocity is proportional to the time related by the acceleration. After 2 seconds, velocity is increased by the same amount, 9.8 meters per second, and at 3 seconds it's increased again by the same amount, 9.8 meters per second, but all in the downwards direction. And we can see that position increases not linearly, but actually quadratically, based on the equation that I talked about a couple of slides ago, where that's equal to 0 and that's equal to 0. So the position's increasing quadratically. Now, one thing about the ball that's falling is at every single time interval, it's accelerating at the same rate. The acceleration never changes. This is the acceleration due to the Earth's weight, due to the Earth's pull of an object, and it is constant for all intents and purposes for this chapter. Always downward, always 9.8 meters per second squared. Now, if we consider a ball that has been thrown upwards, so we're looking at up and down motion, it's still actually considered free fall motion. Now, the reason for that is because the ball is still accelerating, and it's always accelerating only due to one force. That is the force of gravity, which is, again, 9.8 meters per second squared downwards. Now, I've mentioned that 3 times. Probably kind of important, huh? So, if you think about a ball that has been thrown upwards, once it leaves your hand, there are no forces acting upon it to keep it moving upwards. The only force acting upon it is the force of gravity in the downwards direction. And you've thrown balls upwards. You know what happens. The ball goes upwards kind of fast, and then it slows down, and then it slows down some more. And at some point it turns around. It's no longer moving in the upwards direction. Its y velocity is actually 0. And then the ball starts to fall downward, and it accelerates due to gravity up here. And it moves faster and faster downwards, covering larger and larger distances, moving faster and faster. It's an example of free fall motion because the only force acting upon this ball is the acceleration due to gravity. Always downward, always 9.8 meters per second squared. Even if the ball is not moving in the downwards direction, the acceleration is still in the downwards direction. Now, this shows that graphically. It shows the position, y. Again, I'm using y now instead of x because we're talking in the up-down. If we look at the y position, and here you are, you're on top of the building, you throw the ball up, hey, it's going to go up. It's going to go up, what, maybe, I don't know, 12, 15 meters or so. At that point, the ball stops moving. It has a y velocity that is equal to 0. it's not moving. Again, the slope of this guy right here, the slope of the position versus the time, is the velocity, and at the very tippy top, the y velocity is 0. So looking at our y velocity versus time chart right here, we see that there is initially a positive velocity, right, 15, and this velocity constantly changes, constantly being the key word. It's constantly changing because it's under a constant acceleration, and at some point right here, the constant velocity is equal to 0. That's when, again, that's when it turns around. And then the slope of this guy, the position versus the time, changes. Now the slope of this guy is negative, and here the velocity is negative. Now again, that doesn't mean that it's moving backwards, it just means that it's moving in the downwards direction, in the negative y direction. And the slope is still constant. Again, that means that this object is experiencing a constant acceleration, and the acceleration is always in the same direction. It's the negative direction, the downwards direction, towards the Earth. Last but not least, we can consider the case of a car that has an acceleration that is not always constant. And hey, in the real world, that's the case. You know, you're at the stoplight, you hit the gas, you accelerate, the car shifts. You slow down a little bit, and then you pick back up again, you accelerate some more, the car shifts, you slow down a little bit, and then you accelerate some more. Now, that's more of a real-world type of acceleration. Fortunately, in this class, I'm not going to give you that type of problem because it becomes a little bit difficult. But remembering how the acceleration is the change in velocity due to the derivative of the velocity with respect to time, and that the velocity is equal to the derivative of the position with respect to time. Now we know in calculus speak we can actually integrate this with respect to time, and we can integrate that guy with respect to time, and the integral of velocity turned out to be position. Now the integral of velocity with respect to time is going to be equal to the integral of the acceleration with respect to time, and the integral of the acceleration with respect to time, so this guy right over here, is simply going to be the velocity. And what that means is if we look at the acceleration versus time graph, the integral means the area under. So if we're looking between two time periods, say t1 and t2, the area under that graph is going to be the integral of the acceleration, and that guy right there is equal to the velocity. Now, if we're talking about doing this using constant acceleration, it becomes a lot easier. If we're talking about it with non-constant acceleration, as in the case down here, then the calculus itself becomes extremely hard. We have to do it graphically, more likely than not. Doing it in the case of constant acceleration, then it works out algebraically quite well, and we have equations that already deal with that. Again, I'm not going to give you this type of problem. This is just something for you to keep in the back of your head for when you do take calculus, or when you get to the part of integrals when you come to calculus.